Hi everyone, welcome to today's tutorial where we'll learn how to solve a linear Diophantine equation using MATLAB. Sounds complicated? Don't worry, it's actually a fascinating journey into the world of integers and equations. First, let's get clear on what a linear Diophantine equation is. A linear Diophantine equation in two variables is of the form ax plus by equals c, where a, b, and c are integers, with a and b being non-zero. The unique thing about these equations is that they only have integer solutions, meaning both x and y must be whole numbers. The name comes from Diophantine of Alexandria, a mathematician who studied these equations way back in the 3rd century AD. And while they may seem ancient, linear Diophantine equations are still highly relevant in modern number theory. Since there are two variables but only one equation, these equations either have no solutions or infinitely many. The condition for a solution to exist is that the greatest common divisor, GCD, of a and b must divide the constant c. If a solution exists, it can be represented parametrically. Now let's break down the code step by step. We declare a function named solve LDE that accepts 3 inputs and returns 4 outputs. The inputs a, b, and c represent the coefficients of the LDE ax plus by equals c, while the outputs x and y are the general solutions of the equation. The function also returns a parameter and a condition, which we will explain later in the video. Since we are solving an equation, we first use the sims function to create symbolic variables x and y and set the assumption that they are integers. Then we define the LDE as a symbolic equation called EQN. Next, we use MATLAB's built-in GCD function to find the greatest common divisor of the x coefficient a and the y coefficient b, storing it in a variable named d. The MATLAB mod function returns the remainder when dividing c by d. This allows us to check if c is divisible by the GCD d. Using an if statement, we test whether the remainder is 0. If it is, the equation is solvable in integers according to the theorem, otherwise it's not solvable. We then use the solve function to solve the LDE, passing it the symbolic equation EQN, the variables x and y, and the name-value pair argument return conditions true. The return conditions is a flag that returns parameters and conditions. If true, it provides parameters and conditions under which the solution is valid. I hope you now understand what the terms parameter and condition refer to. Next, we use these general solutions, parameters, and conditions to generate some positive solutions for the LDE. The assume function ensures the condition is valid. We store a system of inequalities where x and y must be greater than 0 in an array named restriction. Let's elaborate on what we're doing here. X and y are symbolic expressions containing a parameter. Here, we assume the condition and restrict x and y to be positive. Then we use the solve function to find a valid value of the parameter for this restriction. The result of the parameter is some integer values for which both x and y are positive integers. These integers are stored in an array named sulk. We then use isEmpty to check if sulk contains any solutions. Some LDEs may not have positive integer solutions, so this check is important. If solutions exist, we proceed to find them. Otherwise, we print that there is no positive integer solution. The fprintf function is used to format and display the results on the screen. The length function gives us the number of elements in sulk, and the for loop iterates that many times. Each value of sulk is substituted in the place of the parameter in the general solutions x and y using the subs function, and the results are printed in each iteration. Finally, we call the function at the beginning of the script and run it. Thanks for watching. If you enjoyed this tutorial, don't forget to like, share, and subscribe for more coding and math content. See you in the next video. This is Tough Nut, signing off. Happy coding.